Welcome to the second part of trigonometric form of a complex number, where we're going to talk about Demoivre's theorem and how to find roots of complex numbers. All right, so on example 5, let's talk about finding powers of complex numbers. So if we define z to be r cosine theta plus I sine theta, which is a trig form of a complex number, what happens if we look at powers? So like if I want to look at z squared, that means we're going to take r cosine theta plus I sine theta times itself. All right, well, we just learned in the previous video that when you multiply them together, we multiply the moduli together, so that's going to give us an r squared. And then I add the arguments. So theta plus 2 theta, or excuse me, theta plus theta is 2 theta. So basically this z squared is equal to r squared cosine 2 theta plus I sine 2 theta. All right, so now let's consider z to the third. And I could write this 3 times and multiply it out, but can't we consider and break it down that it is z squared times z to the first? So I can take my previous answer of r squared cosine 2 theta plus I sine 2 theta and just multiply by another z. So times r to the first cosine theta plus I sine theta. And when you multiply them together, we multiply the modulus together, so we get r cubed. And then I add the arguments, so that's going to give me a cosine 3 theta plus I sine 3 theta. And some of you might be saying, hey, I kind of am starting to see a pattern here. So let's think about z to the fourth. That is z to the third, my previous answer, times another z. So I'm going to take r cubed cosine 3 theta plus I sine 3 theta times another z. And what do you know? When I multiply the modulus together, I get r to the fourth, and this was z to the fourth. And when I add the arguments, I get a 4 theta. So while this is not a proof, this is a pattern. So to be clear, this is not a proof, it's a pattern. If I asked you, well, what is z to the 10th? Do we really want to go through all of those iterations? Well, let's look at the pattern. We could say it's going to be the modulus to that power, and then the argument times the power. And friends, that is essentially Demoivre's theorem. So again, we didn't prove it. We looked at it via a pattern. So we have Demoivre's theorem. And it says, if you have r cosine theta plus I sine theta, all right, so we have the trigonometric form of a complex number. And what is important, this is huge, n has to be a positive integer. So we don't count 0. We're saying 1, 2, 3, 4, and so on. This is important because the back half of this video talks about when n is rational. And we have to do something different with Demoivre's theorem. Then all you have to do is, if you're taking this complex number to the nth power, where n is 1, 2, 3, or 4, some positive integer, then it is equal to r to that power, and you multiply the argument. All right, so let's use Demoivre's theorem to find the indicated power of the complex number. We're going to write the result in standard form. So that's important. The final answer is in standard form. That implies that it's got to be an a plus bi form, note trig. Now, in Demoivre's theorem, it has to be in trig form in order for us to apply the theorem. This is in trig form. You're going to have some homework where you're going to have to convert it first. But we're going to now use Demoivre's theorem, and we're going to take this complex number to the 12th power. So this means I'm going to take the modulus of 2 raised to the 12th, and I'm going to take the argument of pi over 2, and I'm going to multiply it by 12. All right, so to simplify, this becomes the cosine of 6 pi, and I don't have to do the math again. It's the same. And because this is being asked for a final answer in standard form, we need to evaluate the cosine of 6 pi and the sine of 6 pi. So let's think about my unit circle. This is 2 pi, 4 pi, 6 pi. I'm at the point 1, 0, so my cosine is 1, my sign is 0. So this is 2 to the 12th times 1. If this was a non-calculator portion of the test, I would tell you to just leave it as 2 to the 12th. But if you pop it into a calculator, we get 4096. So this trig form of a complex number to the 12th power is actually the real number, 4096. Welcome to example 6, where we talk about roots of complex numbers. So hold on to your hats. This is kind of an abstract concept. Remind yourself that you can pause, rewind, and I'm going to be upfront. Even if I am your virtual teacher, who knows, this is definitely something that probably I would want, some synchronous support kind of going through. So we'll do our best. Let's see if we can get through this. All right. We know by Demoivre's theorem that this works when we want to find powers of a complex number when n is a positive integer. And we previously just talked about this problem. 12 was a positive integer. So we took the modulus to the power, and then we took the argument times the power. Okay, but that only worked when n was a positive integer. Now, if I want to take z to the 1/2, if it's rational, what does that mean? It means it's a root. I want you to find the square root of a complex number, or the third root of a complex number, or the fourth root of a complex number. It's pretty abstract. Like, we want to find the cube root of some type of complex number, or this is what it's going to look like, right? If, sorry, it shouldn't have that in there. If we wanted to talk about this in trig form. So finding roots, this part is what's going to be kind of interesting. All right, here we go. The complex number u equals a plus bi is an nth root of the complex number if u to the n is equal a plus bi to the n. So we're saying, okay, we can have some sort of complex number be the root of a complex number. Keeping in mind a complex number can be a real number portion, an imaginary piece, or obviously adding the two. But all right, so I want to find z to the 1/2. So what we're saying here is that I would take r to the 1/2, written as the square root of r. And friends, we are going to continue Demoivre's theorem by we would take 1/2 of the argument. Okay, I just was picking 1/2, friends, as just some arbitrary rational number that you were comfortable with. But here's the problem. You're talking about roots, not powers. So we have to account for all possible angles that would satisfy that argument. Think about when you take the square root of 4. If I have x, so think about this equation. If I have the equation x squared equals 4, and I take the square root of both sides, it's not just 2, it's plus or minus 2. We have to account for all possible angles that satisfy the argument. So this is going to mean all your coterminal angles would be arguments of the nth root of z. So this is what is going to be this extra step when you're finding roots. So again, to be clear, what we're about to embark on does not apply to a problem like we did in example 5. In this problem, we had 12. 12 is a positive integer. It is not rational. What we're about to do is when we are being asked to take some sort of complex number and we are raising it to the 1/3, the 1/4, the 1/5. This is when the following kicks in. Since cosine and sine have a period of 2 pi, we can conclude that this is the nth root of a complex number. All right, hold on to your seat. You're like, holy cow, what is all of this? All right. For a positive integer n, the complex number z equals r cosine theta plus I sine theta, it has n distinct nth roots. You guys, we are guaranteed that by the fundamental theorem of algebra. Remember when you solved problems like x to the 4th plus x to the 3rd plus x squared plus 1, and you wanted to solve for the roots? Highest exponent was 4. So while you might not have 4, and they might not all be real, you were guaranteed 4 roots of that equation, correct? So we are guaranteed as well by the fundamental theorem of algebra that if I'm asking you to find the 4th roots of a number, you should have 4 answers. If I'm asking you to find the 3rd roots of a complex number, you should have 3 answers or 3 roots. I'm going to go ahead and explain this 2 pi k business when we actually do a problem. K is sort of like your n's. It's just how they've assigned their variables. N is referring to the roots, and K is what I call your angle generator. So I will also explain this K is equal to 0, 1, 2, and n minus 1 business. Let's jump into a problem. Okay, here we go, friends. We want to find the fourth roots of negative 4. All right, so here we go. Negative 4, if I do a real imaginary axis, negative 4 would be located right here. Demoivre's theorem only works when I am in trig form. So this is an example of the problem is not asking you to convert to trig form, but you have to go into trig form in order to use Demoivre's theorem. So in trig form, what is my modulus? Well, your modulus is your absolute value from 0. So that is 4 units. And what is this angle? That angle is pi. All right, so 4 cosine pi plus I sine pi. All this is a way of writing negative 4 in trig form. All right, moving on. What the question is asking, the question wants you to find the fourth roots of 4 cosine pi plus I sine pi. That's what it's asking. Well, instead of writing it in radical form, let's go ahead and write it in rational exponent form. So that is going to imply 4 cosine pi plus I sine pi all to the 1/4 power. All right, this is where things are going to be different because you would have to identify that this is a root problem, not a power problem. It's a root because we have that rational exponent. So I'm going to start this off like we did Demoivre's theorem earlier. The modulus is going to get the power and leave a little space. I'm going to take pi times 1/4. All right, so that's my pi times 1/4, pi over 4. But we have to generate all of its coterminal angles. Because if I just write this, it's one root. We need an angle generator to give us all of our roots. So this is how I choose to write it. It's also going to be that 2 pi k over 4 as well. Why 2 pi? Because cosine and sine are 2 pi periodic. Okay, how are we doing, friends? Okay, so let's discuss how we go from here. From here, I have this 4 to the 1/4. All right, this is something hopefully you remembered from when you learned about rational exponents. You need to try to reduce the index. Notice how 4 is a perfect square. So the fourth root of 4 is equivalent to the square root of 2. So when k is equal to 0, this is where I'm coming back to the definition. K equals 0, 1, 2, and n minus 1. I don't know that you need to memorize that. If we're doing fourth roots, if you do the fundamental theorem of algebra, we have to do 4 iterations. So when k is equal to 0, this is just going to be root 2. The cosine of pi over 4, this goes away, k is 0, plus I sine pi over 4. Okay, when k is equal to 1. That means you're going to add 2 pi over 4. So this is going to give me root 2, which is my modulus, the cosine of 3 pi over 4 plus I sine 3 pi over 4, because pi over 4 plus 2 pi over 4 gives me 3 pi over 4. Now, you are welcome to keep doing like when k is equal to 2 and k is equal to 3, but I just keep adding 2 pi over 4 to my previous angle. So my third root, which is when k is equal to 2 because we're starting with 0, so that's going to be root 2. The cosine, if I add 2 pi over 4 to 3 pi over 4, I get 5 pi over 4. And last but not least, when k equals 3, which is n minus 1, it's 4 minus 1, we wanted 4 roots, I get root 2, the cosine, when I add another 2 pi over 4 to 5 pi over 4, I get 7 pi over 4. You need to read the directions. If the problem asks you, oops, let's get, I got to get that 4 in there. There we go. If the problem says trigonometric form, you're done. These are your answers in trigonometric form. But if the problem wants it in standard form, then I have to evaluate each of these exact values and then multiply them by root 2. So that's one of the reasons I simplified to root 2 instead of using the 4 to the 1/4. So the cosine of pi over 4 is root 2 over 2. The sine of pi over 4 is also root 2 over 2. When you distribute, you're going to get 2 2's, which is 1, plus I. So that is your standard form root. Next, 3 pi over, cosine of 3 pi over 4 is a negative root 2 over 2. So when I distribute, I get a negative 1 plus I. Here, I'm going to get a root 2. Cosine is negative in the third quadrant, as is the sine. So we're going to get negative 1 minus I. So standard form, standard form, standard form. And then here I'm going to get root 2 times a positive root 2 over 2 minus I root 2 over 2. And this gives me 1 minus I. Those are your 4 roots of negative 4. So why is this cool? Please don't shut me off now. I think that this is really what ties this whole unit together. We're going to relate how Demoivre's theorem, specifically with roots, ties in with something you know from Algebra 2 trig. So let's go back in time, and if you were going to solve this equation, and I asked you to find all possible roots, not just the real ones, you can't just take it, plop it to the other side, take a cube root and be done. You had to factor it using a sum of cubes. So we're going to have x plus 1, x squared minus x plus 1 equals 0. When we use the zero product property for the first factor, we get x is equal to negative 1, and that is a real root of x cubed plus 1 equals 0. But when we had to find the remaining imaginary solutions, we have to use quadratic formula. So we use x equals the opposite of b plus or minus the square root of b squared. That did not print well. Let's redo that. Of b squared minus 4 times 1 times 1 all over 2a, which is 2 times 1. So that gives me 1 plus or minus, negative 1 is 1, minus 4 is negative 3 all over 2. And we get 1 plus or minus I root 3 over 2. And those were my 2 imaginary roots. And by the fundamental theorem of calculus, we were guaranteed 3 solutions. And in this case, we have 1 real and we have 2 imaginary or complex numbers. So, how does this relate to what we just learned about Demoivre's theorem? Well, even though in Algebra 2, I asked you how to solve this equation, I could ask you that same information by saying, what are the third roots of negative 1? Very similar question to what we just did. We did the fourth roots of negative 4. What are the third roots of negative 1? Because obviously, if we would pop this one to the other side and take the cube root, that's what we're asking for. So we're going to find these answers using Demoivre's theorem and using the extension for roots. So what's the first thing we have to do? We have to convert negative 1 into trig form. So we have a real and imaginary axis. So negative 1 is on the real axis. It's got a modulus of 1, and that angle is pi. So negative 1 in trig form can be written as cosine pi plus I sine pi. Well, I am asking you to take this to the 1/3 power. So by Demoivre's theorem, we take 1 to the 1/3 power, which is just 1. I'm not going to write it. And then I'm going to take the cosine of pi over 3 plus my angle generator of 2 pi k also over 3 plus I sine pi over 3 plus 2 pi k over 3. So when k is equal to 1, or excuse me, k is equal to 0, then you don't have to add that 2 pi over 3. We are just left with the cosine of pi over 3 plus I sine pi over 3. Now, when k is equal to 2, or excuse me, is equal to 1, which is the second iteration, all I do is add 2 pi over 3 to my previous argument. Well, 2 pi over 3 plus pi over 3 gives me 3 pi over 3, which is pi. And when I do my last iteration, which is k equals 2, and this is why I just feel compelled to write those because they're per definition, but if I was doing my own work, I would just keep adding 2 pi over 3 to my previous argument. My previous argument was 3 pi over 3, so if I add 2 pi over 3 to that, we get 5 pi over 3. So if we're finding 3 roots, you stop when you get your third iteration. So I've got the cosine of 5 pi over 3 plus I sine 5 pi over 3. So you might be sitting there going, wait, what the heck? This doesn't look anything like what we solved before. I'm having a pinching in problem here. Lord iPad. There we go. All right. So if you look, if we compare the answers that we gave algebraically, friends, those are in standard form. What we have right now is not standard form. We have trig form. So let's convert our trig form into standard form. So when I do k equals 0, the cosine of pi over 3 plus I sine pi over 3, I get, well, the cosine of pi over 3, let's think about that up here. You're talking about pi over 3, and I've got a short x long y. Short x long y. Well, if we look at this statement, can't I think of this as 1/2 plus root 3 over 2i, and as 1/2 minus root 3 over 2i? And how about that? We got a match. This solution matches this solution. All right, let's go to the second iteration. The cosine of pi, that's at -1, and sine of pi is 0. So we get -1. And by gosh, we have a match. We got -1 even when we did it by factoring. And I bet you can kind of see ahead. The cosine of 5 pi over 3, we're in quadrant 4, so I'm still a positive 1/2, but my sign is negative. And that, my friends, is a match. So that's how Demoivre's theorem, I'm trying to tie that into something that you did into trig. You are now ready to continue your Unit 2, Lesson 3 WebAssign, and I hope you are having a great day.